Hi everyone, so this is the video for chapter 6, lecture 3. It will be the last lecture for this chapter. So if you guys remember, the last time we went over the ideal gas law, right? So PB equals nRT, and then we did problems involving that, and then we derived equations for molar mass, density, right? We did problems involving that. So in this next part, we're gonna move on to collecting gases over water, and then we'll do stoichiometry involving gaseous reactions. And then we'll go over kinetic molecular theory, and we'll end there. Okay, so what is collecting gases? Well, it is a gas chapter, right? So in reactions where gas is being evolved, what if we want to measure how much gas we made as the product? Um, it's easy when it's a solid, right? Because you just collect the solid and you mass it. But if it's a gas, it's like flying away. So how do we actually, collect the gases and then analyze it, right? One of the methods is called collecting gases over water. Okay, so looking like this. Okay, so let's say you have a reaction where you take zinc metal and HCl. This is a redox reaction that the zinc will reduce the HCl, and it will become hydrogen gas. So the hydrogen gas is now flowing through this tube, and this tube is routed into an upside down beaker full of water, right? So the gas basically displaces the water out, and then you can actually measure the volume, right? The headspace here of gas. And now we know, right, from PV equals nRT, if you have volume and temperature and pressure, then you can get moles of gas, right? So here you'll be able to measure the volume of hydrogen gas, right? But a tricky thing too is that since this was collected over water, you also have water vapor in this space, right? Not just hydrogen gas. So you need to actually subtract out the water vapor first to just get the hydrogen gas and then figure out how many moles of hydrogen you produced, right? So how do we figure out how much water, gaseous water or water vapor to subtract out? Um, is we'll need to figure out what is the vapor pressure of water at a certain temperature. So the vapor pressure of water, which is defined as like what is the gas layer above a water a liquid water body of water, right? There's always a vapor above that. And so that's what the vapor pressure is. And it's dependent on temperature. So the higher the temperature, the higher the vapor pressure of the water, right? So there is a table that you can use in order to figure that out, right? So as you can see here, right, as you increase the temperature, you increase the vapor pressure of the water. And the pressure here is measured in millimeter mercury, all right? So up to from 0 to 100 degrees Celsius, you can figure out what is the vapor pressure of that water, and then you subtract it out from um you know the total pressure, and so you just have your gas, right? So let's do an example problem. In order to determine the rate of photosynthesis, the conversion by plants of carbon dioxide and water into glucose and oxygen, the oxygen was emitted the oxygen gas emitted by an aquatic plant is collected over water at a temperature of 293 Kelvin. So I'm gonna write that down, right? T is 293 Kelvin. And a total pressure of 755.2 millimeter. Okay. And then it says over a specific time period, a total of 1.02 liter of gas is collected. So it's giving me a volume, right? So that little space, right, that's trapped, that gas space is 1.02 liter in volume. And now it's asking me what is the mass of oxygen gas that forms. So we're looking for grams of oxygen, right? Oxygen gas, right? Remember, oxygen is a diatomic, Hofbrinkel, right? So O2. Okay, so let's go to the board and we can figure this out. All right, so P total, remember, is doesn't just contain hydrogen gas, but also water vapor, right? Trapped in that bubble. So it's going to be the partial pressure of hydrogen gas and the partial pressure of water, right, is equal to P total. Okay. So now we can go to that table, because that table, right, at 293 Kelvin, what is that in Celsius? Minus 273, that's 20 degrees Celsius. So you go to the table and say 20 degrees Celsius, oh, that's 17.55 millimeter mercury. Okay, so that's what we get for partial pressure of water. Okay, so then, okay, we should be able to figure out what the partial pressure of hydrogen is. We just take the total pressure, which is 755.2 mmHg, subtract out water's vapor pressure, right? 17.55 millimeter. Okay, and that should give us 737.55 millimeter. Okay. All right, so now we have a pressure, right, guys? We have pressure, we have a temperature, and we have a volume. From PV equals nRT, we're able to solve for moles, right? Okay. But before we can do that, remember, we need to change our pressure into atmosphere. So 1 atm up top, 760 mmHg at bottom is 0.9706 atm. Okay, so remember, we want moles of, it wants us to figure out grams of oxygen, right? But first we need to get to moles. So it's a gas chapter, right, guys? PV equals nRT here, because that's the equation that has moles in it. So solving for moles, N is equal to, divide by RT on both sides, PV over RT. The pressure has to be in atmosphere, right? So that's why we converted it. Volume is in liter already, wonderful, so 1.02 liters. Divide by R, 0.08206 liter ATM per kmol, times the temperature, which is 293 Kelvin. So Kelvin, as you can see, cancels out. Liter cancels, ATM cancels, and we have 1 over mole, which is mole, right? So I have 0.04118 moles. Remember, don't round yet, so keep many sig figs. That's moles of O2, right, guys? And we need grams of O2 though, so one more conversion. I'm gonna go 1 mole of O2 on bottom and 32.00 grams of O2 on top. So that's gonna give us 1.32 grams of oxygen gas. Okay. 3 sig figs, right? Because of these numbers. Okay. All right. Go back to our slides here. Okay, so that's how you do it. Whenever you have anything collected over water, just make sure that you grab a number off of this table here for the vapor pressure of water, and you subtract it out from the P total to get just the partial pressure of your gas that you're interested in, right? The gas that's being formed. All right. Okay, so let's go to the stoichiometry now, part of gases. So as you notice, every time that we introduce a different state of matter, like last time we went to aqueous, right? We were at aqueous state of matter, solution chemistry, right? We expanded on the roadmap. Okay, so we're gonna do the same thing here. Now we're at gases, right? How do we deal with stoichiometry for gas? So we're gonna expand our roadmap now even more. Okay. So you guys look familiar, right? So last time we introduced liter of A in the aqueous state, right? With molarity of A, you can get to mole A. Okay. And these were old news, right? If you start with a solid, right, then you have grams as your unit, and you use molar mass to get to mole. Okay. Atoms and molecules of A use Avogadro's number to get to mole. Okay. But then we went to solution chemistry, right? So solution chemistry, you can't just measure anything out. So you have to measure it out by volume. So you have, some liter of a solution of A, and if you know its molarity, you get to moles. Okay. And it's the same on the other side, right? Well, now we're in the gas state, aren't we? We're not in solid state, we're not in aqueous state, we're in the gas state. So in the gas state, we can't just mass out a gas on a scale, okay, and fly everywhere, right? So what do we need? We need pressure, we need a volume and temperature. We need three things to actually get to moles of A, right? And we use which equation, guys? PV equals nRT, right? So solving for N, PV over RT, okay? And so that is why we need all three parameters of pressure, volume, and temperature. If those three things are known, then we can get from those units to mole of A, right? And on the B side, same thing, right? So now it's looking like a very complete roadmap with all states of matter on it, right? That you'd ever encounter. Okay, so really this is the complete roadmap that you're gonna see, right? So let's go and do some example problems here. Oh, and also, if you guys remember from last lecture, when gases are at STP, remember what STP is? Standard temperature and pressure. If you guys don't remember this, just watch that section of the last lecture. For any gas, okay, regardless of the gas, 1 mole is equal to 22.4 liters at STP. Okay, so this is really useful in stoichiometry. If your problem says at STP, you should be like, thank you, because now you don't need to use PV equals nRT. You can just go straight from volume to mole. You see that? Right? So if 1 mole takes up 22.4 liters, right? Then if I have 44.8 liters, then I have 2 moles, right? So it's really quick way to convert between moles and volume if you had STP, right? So keep that in mind, right? For problems like these. So they'll ask you, how many grams of water form when 1.24 liters of gas, hydrogen gas, at STP completely reacts with O2? And your balance equation is 2H2 plus O2 goes to 2H2O. Okay. All right, so let's do that. Just gonna just quickly write the equation on the board. Okay, and also to summarize what it wants from us, right? It's saying 1.24 liters of H2, and this is at STP, is going to react. How many grams of water forms? Okay, so H2 is a reactant, right? And this problem looks like it's not a limiting reactant problem because there's plenty of O2 to react there, as implied by the problem, okay? So all you have to worry about is just doing the one stoichiometry problem. So our plan, right? And we know since it's at STP, let's write this down already. 1 mole is equal to 22.4 liters. Okay, so just to have it right there for us to use. So here's our plan. We start with liter of H2. Okay, we can go to, because since it's at STP, we'll go straight to moles of H2. And then it's a stoic problem, right? So mole A to mole B. This is mole A. Which one's mole B? Grams of water. So moles of H2O, and it wants grams of H2O, right? So the mechanics, they almost identical, right, to what you've been doing, stoichiometry, right, motor mole ratio. All right, so execute. We got 1.24 liters. Now we can take 1 mole on top of H2, and 22.4 liters of H2 is on bottom, right? Okay, and then molar ratio. We want moles of water on top because that's what we're going to. And there's a 2 in front of water, so 2 moles of water over 2 moles of H2. Okay, that makes sense, right? And then grams of water. So 1 moles of water on bottom. 18.02 grams of water on top. Right? Okay. Let's see what we get. We sig figs 0.998 grams of H2O is produced. Okay, let's see if we got the right answer there. Right. Okay. And then let's do this one. Methanol can be synthesized by the reaction. CO gas plus 2H2 gas goes to CH3OH gas. What volume in liters of hydrogen gas at a temperature of 355 Kelvin and a pressure of 738 millimeter mercury is needed to synthesize 35.7 grams of methanol? Alrighty. Let me write all that, and then we can solve. So, the equation is CO gas plus 2H2 gas goes to CH3OH gas. Okay. What volume in liters of hydrogen gas? Temperature is 355 Kelvin. Pressure is 738 mmHg. Oh, and you see, when you see millimeter mercury, and you know that you're going to be doing stoic, turn it into atmosphere, right? And then needed to synthesize 35.7 grams of methanol. Okay. $35.7. Okay. All right, so here it is, right? All the information. Notice I took the pressure from millimeter mercury to ATM already. I know I'm gonna need that. My temperature is in Kelvin, so great. I'm solving for a volume. Okay. And it's asking, right, volume of H2 that's needed to synthesize 35.7 grams of CH3OH. Okay. So let's write our plan. Right, what we're given is grams of CH3OH, and we're asked to back calculate how much hydrogen would be used to obtain that. So grams got to go to moles, right, of CH3OH. Okay, and then that's mole A. We need to cross the bridge to mole B, right? So molar mole ratio to get to mole of the other one is being asked hydrogen. Okay. Okay, and here, right, we don't have at STP, so we can't use that. We're gonna have to use PV equals nRT, right? So moles of H2 go to volume of H2 in liters. Okay, so let's execute. We have 35.7 grams of CH3OH. Take 1 mole of CH3OH on top. And then let's calculate that molar mass. Yeah, 32.04 grams of CH3OH on bottom. Right, and then molar-mole ratio. Okay, so we want H2 on top. So look at that number, 2 moles of H2 to 1 mole of CH3OH. And then let's calculate how many moles of H2 at this point. Two 2.228 moles of H2. Okay. But it's not asking us for moles, it wants some volume. So how do you go from mole to volume? In gas phase, use your ideal gas law, right? PV equals nRT. So PV equals nRT, and you're being asked to solve for a volume, right? So V is equal to nRT over 8. Okay. So what is moles? 2.228. R is 0.08206 liter ATM per kV. Times the temperature, 355 Kelvin, over the pressure, which is 0.9711 ATM. Okay. All right, you guys agree? So that's the setup, right? And then mole cancels, Kelvin cancels, ATM cancels, and we'll get 66.9 liters of H2. So we're saying 66.9 liters of H2 is needed in order to synthesize 35.7 grams of methanol, which is the product, right? All right, let's go back to the slides. Yep, got the right answer. Okay. All right, let's do this one too. All right. In the reaction shown here, 4.58 liters of O2 forms at the pressure 745 millimeter mercury and a temperature of 308 Kelvin. How many grams of silver oxide decomposed? He2O. Okay, so He2O, as you can see, is on the left side, right? It's a reactant. And what's given to us is 4.58 liters of oxygen forms. Okay, so that's the product. All right, so let me write this down. Okay, pressure 745 millimeter mercury, temperature 308 Kelvin. All right, so there's that. Okay, so we got how many grams of He2O decomposed to 4 and 4.58 liters of oxygen, right? So our plan, we start with liters of oxygen. That's got to go to moles of oxygen, right? Based on our roadmap. Okay. And then moles of the other thing, which is He2O, right? So that's A and that's B, right? Mole A, mole B. And then we can figure out grams of He2O. Okay. All right, so let's see if we have everything we need. Oh, again, some millimeter mercury. Let's convert that to ATM. We know we're gonna need that number later. So we might as well do now. 0.9803. Okay. All right, let's execute. So we got 4.58 liters of O2. We need to get this to moles. So we're gonna have to use PV equals nRT, right? From PV equals nRT, solving for mole, it's PV over RT, right? So the pressure is 0.9803 ATM times the volume, which is 4.58 liters divided by R, 0.08206 liter ATM per kilomole, times the temperature, which is 308. Okay, you'll see the setup there, right? To get us the moles. So that ATM will cancel, liters will cancel, Kelvin will cancel. It's 1/1 mole. So 0.1776 moles of O2. Okay. And now we can continue, right? We have mole of O2. To get to moles of He2O, we need mole to mole ratio, right? So 2 moles of He2O on top, right? This is from here. And 1 mole of O2 on bottom, right here. Right. And then to get to mass, we need the molar mass of He2O. Which is 231.74 grams of He2O on top and 1 mole of He2O bottom. So what is that equal to? How many sig figs? We got 3, right? So 82.3 grams of He2O. Okay. And let's go back to the slides. Okay, there's another problem issue as well that you guys can practice, right? Oh, and this one SP, we already solved for earlier. Okay, so maybe we can do another one. Yeah, how about this one at the bottom? How many liters of oxygen at STP are required to form 10.5 grams of water? And then that's your balance equation. So how many liters of O2 at STP to form 10.5 grams of water? H2 gas, gas. Alrighty. All right, so again, we know, oh, it says at STP, yay, right? So then we just write that equivalency. 1 mole is taking up 22.4 liters, right? Doesn't matter what the gas is. And then we write our plan. We start with grams of water. right? We're trying to back calculate to see how much oxygen is needed to form 10.5 grams of water. So grams of water, we need to convert it to moles of water. Okay. And that's mole A now, right? We get to mole B, which is asking about O2, right? Moles of O2. And then from there, liters of O2. Okay. So we'll start at 10.5 grams of H2O. 1 mole of H2O on top, right? And 18.02 grams of H2O. Get to the mole to mole ratio again, right, guys? So look at the balance equation. We want O2, right? We want 2 moles of O2. That's a 1 up there, 1 mole of O2. And then we want to cancel out the water. So there's a 2 in front of the water. That's 2 moles of water on bottom. Okay. And then let's get that. Oh, at this point now, we can use this, right? We realize, oh, I don't need to use the PV equals nRT because I'm at STP. I mean, I could use it. It would give me the same answer, but it's a lot more cumbersome, isn't it? So at STP, I already have this equivalency. I could just straight go 1 mole of O2 on bottom, right? Takes up 22.4 liters of space. So right there gets me straight to liters of O2, which I'm asked for, right? So that's why at STP, it's kind of nice. It's a lot easier to do the calculation. So 6.53 liters of O2 is the answer there. Yep. Okay, let's go back to our slides. All right, so now the last part of this chapter is going to be over the theory, right? The theory of gas. It's called kinetic molecular theory. It's the theory that is holding this whole thing together of the ideal gas law, why we can use the ideal gas law to do these calculations. Now it's a model, right? Remember, theory is a model. And here the gas is modeled as, you know, we're making a lot of assumptions about the gas. And it's modeled as a collection of particles in constant motion, right? That's how I asked you guys to remember or imagine gas particles at the beginning of this chapter, right? Is that they're very small, they have a lot of space in between them, and they're in constant motion. Also, the KMT, right, the kinetic molecular theory, assumes that the attraction between particles is really negligible. And this is mainly true because gas particles are traveling so fast that even when they collide with each other, there's not a lot of interaction, right? They just bounce back. Okay. So we refer to this type of collision as an elastic collision. So when gas particles hit each other, they don't stick, right? And then really the big assumption is that there's a lot of empty space between the gas particles compared to the size of the particles, right? So that we can just basically ignore the individual volume of the particle. That's why we can have things like at STP, 1 mole of any gas is 22.4 liters, right? It didn't matter the identity of the gas. Also, the KMT says that the average kinetic energy of gas particles is directly proportional to the temperature. Okay. And so if you're at higher temperatures, particles move faster, right? So that when they collide, there's no overall loss of energy. It's an elastic collision completely. They may exchange energy, but there's no overall loss of energy. Okay. So what do we mean by elastic versus inelastic collision? It's like this, right? The billiard ball example on a very smooth pool table is, when you have a collision, they transfer energy, but there's no loss, right? They go bouncing back at the same speed that they collided at, right? Whereas inelastic collision, you do have a loss of overall energy, right? So imagine 2 clay balls now, not billiard balls, but clay balls colliding with each other. That energy actually gets absorbed, they stick together, right? So this is the KMT, right? It's modeling a gas that has this type of collision, the elastic type, right? And that's basically what the ideal gas law is based on, right? And then the nature of pressure, right? This was pressure results from the gas particles colliding against the sides of the container with a certain force, and that spread over what area, right, of the container is, right, the surface area of the container. That's what gives you the pressure, right? So we're going to use KMT now to explain each of the simple gas law on the molecular level, right? And, I really want you guys to, be able to do this on your own as well. So maybe you should talk to yourself as well when you're studying to explain it on the molecular level. Okay? If you can understand it on the molecular level, then it just makes the math easier and you're actually understanding the material better. Okay. So Boyle's law. How do we explain Boyle's law on the molecular level using KMT? Well, Boyle's law says there's an inverse relationship between pressure and volume, right? So that as you decrease the volume, the pressure is going to increase. The reason that when you decrease the volume, you have less surface area, right? And so the particles are able to collide against the wall more frequently, right? Because the walls are closer to them than before. And so that means you have a decrease in area, but an increase in force, right? And so that's why your pressure goes up, okay? Because more molecules will collide with the container at any given instant, right? Because the walls are closer to them. Now, when you increase the volume, what happens? You move the wall away, further away. So the particles take longer, right, to travel to hit the wall. And so it will hit the wall less frequently. Force will go down, right? And also you just spread out the area goes up. So then pressure goes down, right? Avogadro's law. Okay, let's try and explain that. We have a direct relationship between moles and volume, right? So this is kind of like blowing into the balloon, right? That's the example. Uh, at the molecular level, you have moles of gas. The more moles of gas you have, the more force you're gonna get, right? Because more gas particles get to hit the container wall. And so that's gonna increase pressure uh, a little bit, right? But in Avogadro's law, pressure is supposed to stay constant. So what will adjust instead? The volume will expand instead to keep the pressure constant, right? Okay, so those are the three laws, right? That we and Charles' law. Oh, I guess we haven't done Charles' law, so let's do that. So Charles' law is in a direct relationship between volume and temperature. So how do we explain that? Well, as you increase the temperature, you increase the kinetic energy of the individual particles. So they end up hitting the wall faster. And again, that raises the pressure initially, but the pressure is not supposed to change. So what does the volume do instead? It increases as well to alleviate that initial pressure change, right? And so that's why as temperature goes up, volume also goes up, right? And now let's think the other case. As temperature goes down, the particles slow, right? Kinetic energy is less, so the particles slow down. They don't hit the side of the container as hard, right? And so initially pressure drops, but pressure has to be remain the same. So what happens? The volume decreases instead to keep that pressure the same, right? So temperature goes down, volume goes down, right? Yeah, direct relationship. Okay, so next let's talk about how temperature um, uh, uh, and molecular velocities are affecting gas. Okay, so let's look at the kinetic energy equation. Right, Ke. I actually don't like this rendition of it, so I'm gonna show you guys another easier to digest equation. So kinetic energy is equal to 1/2 mv squared. Okay, m is standing for mass, v is velocity, okay, and then Ke is energy, okay. So velocity is in meters per second, okay? And mass is in kilograms, okay? Those are the base units. So this is how the units would work out. If you have a kilogram for mass and velocity is meters per second, but you square that, right? So what you end up is kilograms meters squared per second squared, okay? And this is unit of, we call this actually joules, and that's the unit of energy, okay? Okay, so that's how it works out, right? 1/2 mv squared. Okay, but what we want to analyze with this equation is, okay, notice that the kinetic energy of any gas is constant, right? It's constant with constant temperature, okay? So at one temperature, the kinetic energy of all gases are the same, okay? Which is interesting because each gas is different, right? Each gas has a different mass and they're traveling at a different velocity. So mathematically, what are we saying? If mass times volume squared has to be a constant number, if you increase mass, what do you have to do with velocity to keep this constant? So if you increase mass, you have to decrease velocity in order to keep this number constant, right? So what we're saying is a more massive gas will travel at a slower speed and vice versa. If mass goes down, right, then velocity has to go up to keep this constant, right? So as you go down in mass, you have a faster travel particle, okay? And that's kind of intuitive, right? That's quite intuitive. Something that's lighter is going to travel faster than something that's heavier, right? So think like a quarterback. It's a lot quicker than you. We're huge like linebackers, right? So that works for gases as well. Okay? So if you look at this graph here, you can see that, right? The molecular velocity is on the x-axis. There's a distribution, of course, okay? But you can see that the heavier the gas, so oxygen here, compared to all the other gases, is going to have the highest molar mass, right? 32 grams per mole. Notice that there's a distribution of how fast these oxygens are going, but the peak, right? The fastest ones can go about, what is that? 300, I would say, roughly 300 meters per second, okay? But let's look at hydrogen gas. That's the lightest one, right? Hydrogen is 2.016 grams per mole. At the peak right here, about 1700 meters per second, right? So clearly, you see that the lighter the gas is, the faster it's going to travel, okay? Due to that kinetic energy equation, right? Because they all have to have the same amount of kinetic energy at a certain temperature, okay? So pretty interesting, right? Okay, so from this equation here, the kinetic energy average equation, you can have derive the velocity equation, right? So U right here stands for velocity. RMS is root mean squared. So the root mean square velocity of any gas is the square root of 3 times RT over the molar mass. Okay, so this equation is on your conversion sheet. You don't have to memorize it, right? You just need to know how to use it. So URMS is equal to square root of 3 RT over the molar mass. Okay, so let's do an example problem where we use this equation, and you can see the units that you need to for this equation. It's a little different than your ideal gas problem. Okay, so let's do it. Calculate the root mean square velocity of oxygen molecules. So that's O2. Velocity of O2 at 25 degrees Celsius. Okay. Right, so we're solving for this, right? Square root 3 RT. So what you have to realize here is the R that's used in this equation, it is still the gas constant R, but it has a different unit. Since we're talking about speed, and energy, you're gonna use the 8.314 joules per kmol. Okay, instead of the 0.08206 liter ATM per kmol. Okay, so the liter ATM is an energy unit. Okay, and so it's a joule. So they just converted it, right? And when you do the conversion to joules, it's 8.314. And that's the one that you have to use for this equation, only specifically for this equation, right? So let's, you can just plug it in. URMS is equal to, and remember earlier what I said joule was? 1 joule was kilogram meter squared per second squared. So you can see how this works out as well. Okay, so 3 times 8.314 joules. Let's replace it with kilogram meter squared per second squared. And then per kmol as well, right? So that's the whole thing. Divide by the molar mass. Molar mass of O2 is 32.00 grams per mole. But we want this in kilograms. See, if I have grams, then it's going to be not canceling. So I have to do this in kilograms, which would be 0.03200 kilograms per mole. Okay, right? 32 grams per mole. We have to divide by 1,000 grams to get to a kilogram, right? And so that's why it's okay. So that's the two things you need to keep in mind when you're using this equation, is that your R is 8.314 and your molar mass should be in kilograms per mole, not grams per mole. Okay. And then you can see how the units cancel here. Mole cancel, kilogram cancel. And then we have joules per Kelvin. And then we have to multiply by temperature too, right? Up here. Temperature is 25 degrees Celsius. We're going to change that to Kelvin, 298.15 Kelvin. Okay, right? So 3 times R times T over the molar mass. Okay, so you see how Kelvin cancels. And what do I have left? Meters squared per second squared. But when I take the square root, it will be meters per second, which is a velocity. Okay, so you guys can see how the units work out here. Two point three. Let's see. I think we use 3 sig figs for this. Yep. So 2.32 times 10 to the 4th meters per second. 232,000 meters per second. Okay. Oh, but we have to take the square root. Oops, that's why. So we square root that. What we get is 482 meters per second. I was gonna say that's really fast. Right, so this number was just what was under the square root. And now when we square root, we get 482 meters per second. Alrighty. Okay, there's another example problem too you guys can do. We're gonna skip mean free path, don't worry about it. The only last thing we're gonna go through in this chapter is effusion. There's an effusion equation. So let's discuss that. Diffusion and effusion. So diffusion, you guys already probably heard of. This is the phenomenon where molecules will spread out from a place of high concentration to low concentration. Right, that's what diffusion is, and it'll do that just spontaneously, right? You don't have to stir, you don't have to mix or anything. It'll just do it on its own. Effusion, that's a little bit more different. Okay, so effusion is displayed here. So effusion is if you have, say, a box in a vacuum, right? So you have a vacuum space and all the gas particles are in there. And then you make a very small, tiny hole for which the gas can escape. That's what effusion is. So of course, which gases are going to effuse first? What do you guys think? The ones that travel the fastest, right? Which means the ones that are the smallest. Okay, right? Less massive. So less massive gases will effuse faster. Okay, and so that's why the equation for Graham's law of effusion is only involving molar mass. That's it. That's the only thing that governs how the rate of effusion, right? How fast a gas will effuse is how heavy is it, right? If it's heavier, it's going to effuse slower. If it's lighter, it's going to effuse faster, right? All right, so again, this equation's already on your equation sheet. You just need to know how to use it. Right, rates A over rates B is equal to the square root, the molar mass of gas B over the molar mass of gas A. And then let's do this problem together. An unknown gas effuses at a rate of 0.462 times that of nitrogen gas. Okay, so we need to translate that into a ratio here, right? Because Graham's law of effusion is rate A over rate B. So let's say an unknown gas effuses at a rate of 0.42 times that of nitrogen gas. So, rate of an unknown is equal to 0.462 times that of the rate of N2 gas. Okay, calculate the molar mass of unknown gas. Okay, let's go and do that. Okay, so again, here's the equation we're going to use, right? And this is what the information we translated that first sentence. The rate of an unknown gas is 0.462 times that of the rate of N2 gas. Okay, so what does that mean? The rate of unknown gas over the rate of N2 gas is 0.462. Okay, which then is equal to the square root of the molar mass of nitrogen gas over the molar mass of the unknown gas. Okay, and we're asked to solve for what? The molar mass of the unknown gas, right? So that means we have to square both sides first, right? So 0.462 squared, 0.213, more second, 134 is equal to the molar mass of N2 over the molar mass. And what's the molar mass of the N2? 28.02 grams per mole. So the molar mass of the unknown gas is 28.02 grams per mole. Divide by 0.214. So what's that? $131 grams per mole. That's the molar mass of the unknown gas. Okay. Go ahead and look at your periodic table, guys. Can we figure out what gas that is in the periodic table? Oh, it looks like xenon, doesn't it? Isn't that cool? Okay. So you measure fusion, right, of gases compared to each other. You may be able to figure out what the unknown gas is, right? Just based on how slow or how fast it diffuses. Right? It's pretty cool. All right. Let's go back to our slides. All right. So the last part of this chapter, we're going to talk about real gases, right? So far we've talked about ideal gases. And remember, ideal gas laws assume what? There are no attractions between gas molecules, that gas molecules do not take up space, okay? But for real gases, that's not always the case, right? You can imagine that you can compress a gas so much that there's not a lot of space in between them. So all of a sudden, the gas molecules themselves do take up an appreciable amount of space, right? Or that even no attractions between gas molecules, that's only true if the gas particles are traveling really fast, meaning at high temperatures, right? But then at low temperature, the gas particles slow down enough so that when they do meet each other, there is some attraction to them, right? And so that is going to not give you the same numbers as if you just use the ideal gas law, right? Because some gases are not ideal, or there are certain conditions where gases are not behaving like ideal, okay? So you can see it here in this chart, right? The ideal gas at STP, 1 mole takes up 22.41 liters, right? But if you compare it to some real gases, you see that hydrogen, helium, and nitrogen, ammonia, those ones, more or less, right, adhere to the ideal gas law. It's mainly because they're lighter, right? Look at hydrogen and helium. They adhere most to the ideal gas because they're really light, okay? And so therefore that gas molecules do not take up space, works out, right? But as you go to the heavier gases, right, their individual volume now actually do take up, is significant. So Cl2, for example, is 70.9 grams per mole, is deviating quite a bit from an ideal gas, right? Because it's just heavier, okay? And then the conditions too, right? Ideal gas conditions are high temperatures and low pressures, okay? But once you get to high pressure and cold temperatures, these assumptions kind of fall apart, right? And so let's see how they do fall apart. So at low pressures, the volume of argon is nearly identical to that of ideal gas, right? Of course, we said at low pressures, gases behave ideally, right? But what happens as the pressure increases? That means, what are you doing? You're decreasing the volume. So the gas particles are now closer to each other, okay? Which means the distance in between them is less, right? And so that their individual volume is now, um, more significant than before. And so what that means is the volume of a real gas is actually higher than that of an ideal gas. Okay. And here the picture, you can see that, right? So when you have a lower pressure, not the picture on the left, which also means there's a lot more room, right? There's a lot more gas space. There's a lot more empty space in between the gas particles. So each individual volume is smaller, right? Or negligible. But once you have um, the higher pressure case and everything's closer together, then each individual volume of the gas particles now counts for more, right? And so that's why you see at high pressure, the volume is higher than predicted for a real gas than an ideal gas. Okay, so you see that for argon, right? It starts to deviate from ideal gas as you increase the pressure. Okay. So where does it start deviating? It looks like around here, maybe like 150 ATM. Okay. So that's really high, right? So argon is an ideal gas up to 150 ATM. We're standing at 1 ATM, right? So, you know, for all intensive purposes, right, the ideal gas law works pretty well for argon, okay? But you do see that it deviates, right, if pressure gets really, really high, okay? So van der Waals, German guy in the 1800s, um, he was the one that studied these real gases, right? So he introduced what's called the van der Waals constant in order to correct for the volume of a real gas. So it's like basically a fudge factor, right? So it's a volume is nRT over P. Well, let's add a little fudge factor because we know real gases have a greater volume than ideal gases. So let's add NB to that. Okay, what about the effect of intermolecular attractions? So ideally, right, at high temperatures, because gas particles collide with each other, at such high speed, they're no attraction, right? They just collide with each other and go on their merry way. Okay. However, at low temperatures, what happens? The gas particles slow down. So when they do collide with each other, there's attraction there. So what does that mean for pressure? Well, if the gas particles are spending more time attracted to each other, they're spending less time hitting the side of the wall. So pressure of a real gas is lower than an ideal gas, right? So again, we see that for xenon, right? As you lower the temperature, the pressure of xenon is lower than predicted for an ideal gas. Okay. And you can see that. What temperature would that be around? Like 1,000 Kelvin? Mm-hmm. So we're at like 273 Kelvin. So we're good, right? But if we want to study, um, super cold, so we're here, right? Oh yeah, no, we're like down here, right? So for xenon, we can't, study xenon, at our temperature because it would deviate from ideal gas, and so that's why van der Waals introduce another fudge factor for pressure, right? So subtracting some fudge factor here. Okay, so combining it together, we get the van der Waals equation, which is like the corrected equation for PV equals nRT to account for intermolecular forces and particle volume. Right? And the A's and the B's are already tabulated for you, so you just look it up, right, in order to use this equation. But this is the equation that you would use for a real gas, right, and not just PV equals nRT. Yeah. Okay, so that's it for this chapter. You can see here on this graph, you have behavior of the real gases. Notice, right, as the pressure increases, since pressure increases, the individual volume of each gas accounts for more. So volume goes up. So this PV over RT graph also goes up for most gases, right? And it deviates from this ideal gas pink line here, okay, as pressure goes up. All right, so that's it, guys, for chapter 6. I'll see you guys next time for chapter 7.